Hi, let's get back in the saddle with finding our extreme value theorem for three-dimensional functions. Oops, wrong saddle. We are, of course, talking about this kind of saddle. If you remember, we were looking at criteria if given a surface to figure out if you had a critical point, if it was going to be a maximum, a minimum, or a saddle point. Very similar to what we did in Calc 1. So quick review, and then let's jump in and do some examples. So to review, what we started before was classifying the critical points of a function. First, points are critical points if the gradient is valued at 0. Remember, the gradient being a vector. For that to be the 0 vector, that means both the I and j components have to be 0. So in other words, you're setting up a system of equation where the partial derivative of x and the partial derivative of y would equal 0. Once you've established the x and y values that make this true, you have a critical point. Just like in Calc 1, not all critical points have to be extreme values or saddle points, but any extreme value or saddle point would in fact be a critical point. Hint, that's a fantastic true-false test question. So in order to test what kind of a discriminant is, you first find what kind of critical point, you first find what we call the discriminant. Not exactly the same discriminant as the one from algebra, but kind of similar. So this really relies on our Taylor polynomial, just so you understand where this is coming from. If we zoom in close enough to any point, we could come up with a quadratic that models what our surface is doing. So then based on that, we can determine if we have a surface that is concave up, concave down, or if we have the saddle point. So finding the discriminant, the first step is to figure out if it's positive or negative. Remember, this implies you're plugging in actual numbers for x0 and y0. So your final answer for D should be a number. If the discriminant is positive, that means your surface would be concave up. So your point is a local minimum at that point. If your surface is negative, again, that means when you zoom in on your surface to that one point, your surface is concave down, so you would have a local maximum. And if your surface is, if the discriminant is negative, then you have a saddle point. Again, to clarify both the first points, the discriminant is positive, and you're looking to see what's happening with the second partial of x. If the second derivative of x is positive, that's your concave up local minimum. Second partial is negative, concave down local maximum. If the discriminant itself is 0, less than 0, saddle point. If the discriminant equals 0, that gives you no information. If you have no information, you unfortunately have to do some sort of numerical analysis that can usually be tedious, but just so that we're aware that doesn't tell us anything, we could have an extreme value. So if the function has a global maximum on R, on that region, that means that that function value is bigger than all other function values in the whole region. Global minimum would be that function value is smaller than all other values. Very similar to our extreme value theorem in Calc 1. So a global maximum or minimum could be critical points, just like in Calc 1, and we would have to investigate if they give us a global maximum or global minimum. So how can you tell? In Calc 1, if you recall, if a function was described defined on a closed domain, a certain value of x, then it for sure had a maximum and a minimum at a critical point or on the boundary. We're going to have something similar, but now since our input is the entire xy plane, the domain, our boundary now is not just going to be one-dimensional, but two-dimensional. So you can think of your boundary more as sort of a circular radius going out. That region is bounded if the distance between every point in R and the origin is less than some constant k. So you get something that looks like this. This would be the boundary. Here, this would be on the interior of the region. If it doesn't include the boundary, then the region is not closed. So we do need to include the boundary in order for our region to be closed. So here's an example in the statement of the actual theorem, very similar to in Calc 1. If a function is continuous on a closed and bounded region, this is important. The region has to be closed. Then f has to have a global maximum and a global minimum some point in that region. So here we have this one. This is sort of our counterexample to show why the closed is important. Does this function f have a global maximum or a minimum on this region where our domain is limited to inside the unit circle? So notice that x is bigger than 0, less than or equal to 1. However, it doesn't include 0. It's missing that point right there. So since this region is bounded, but it's not closed, it doesn't contain that boundary point. So this theorem may not apply. And if you investigate this surface, you'll find that this in fact does not have a global maximum, because as this function f of xy is going to go to infinity as I approach 0, right? I can get in as close to 0 as I want. Notice that 0, 0, of course, is not in the domain at all, but I can get in as close to 0 to I want. And the smaller this denominator gets, the bigger my z value, my output's going to get. And I can keep going up as high as I want. It's not ever going to be bounded there. So the closed part is actually important. So let's look at a couple examples of how we're going to practice doing this. And it should be pretty similar, to the practice that you were doing the other day. So not that kind of practice, but getting back on our horse here, let's go through an example. Here's again the reminder. So our first steps are very similar. We have to check if we have a discriminant and try and find the local minimum and maximum. So we're going to zoom down to our first one with global maximum and minimums in example 3. And this handout, the activities as always are on Canvas along with all the solutions if you would like to practice them on your own or check yourself, or perhaps you want to pause here and practice these first and then come back and watch the solutions. So in this case, we have just the contour graphs and we are on closed and bounded regions. Notice it's closed because of the or equals. So I'm including the boundary so they're closed. So in each different contour graph, I'm considering what would be a global max and minimum of this function on and inside the blue square. So in this case, we have 4 different contours and we want to find the global max and min. And something we'll notice, for example, in part A, this one, our minimum is inside and this function keeps growing as I move away from the origin parallel to the x, and then it gets smaller as I move away from the origin parallel to the y. So inside here, this is a saddle point. So I can find, however, in this closed and bounded region, a max and min. Max is going to be as far as I can get away. So it looks like the maximum of value is going to occur at the points 2, 0, right over here, negative 2, 0, and the minimum again here. Noticing these are on the boundary, very similar to our extreme value theorem in Calc 1. Again here, this looks like a plane because they are all parallel contours, evenly spaced with a constant rate of change. Normally a plane would not have any critical points and no local maximums or minimums or saddle points. However, if I force it inside this closed bounded region, I can now find the maximum output and the minimum output. And of course, those will be on the boundaries. So notice the maximum appears to be 6 here on this corner, negative 2 and 2. And the minimum value appears to be negative 6 down on this corner over at 2 and negative 2. I'll let you do the other contour ones on your own. And let's go through one more example with more using a function and going through the steps. So here's another review of finding a local maximum, local minimum, and saddle points. So your first step is to find the critical points. That would be setting the gradient equal to 0. For the gradient to be 0, you set the partials to 0. So first we find the partial of x, which is y minus 2xy minus y squared, and the partial of y, x minus x squared minus 2xy equals 0. We now have a system of 2 equations with 2 unknowns, so we know we can solve it algebraically. You really have to be careful keeping the algebra organized, or it's possible to lose solutions. So in this case, on equation 1, what they've done is factored. Factoring is always a good idea here if you can, and then you can break it up into cases. So here we have one option where y is 0, or where the inside of the parentheses 1 minus 2x minus y is 0. So we have to worry about both of those options. So in case 1, if we let y equal 0, now we put it into the other equation, and that would give us x is 0 or x is 1. So I now have 2 critical points from that one case, the 0, 0 or the 1, 0. Now I have to go back to my original analysis with case B, which was that 1 minus 2x minus y equals 0, or solving for y is 1 minus 2x. Plugging that into the other equation wherever I see x, I get 2x, x minus x squared minus 2x times 1 minus 2x equals 0. Combining all my like terms and factoring, we're going to get that x is 0 or x is going to be 1/3. Again, that's 2 more solutions that I have to now go back and find out what the y is. Remembering that y is 1 minus 2x in this case. So plugging that in, I get x is 0 goes with y being 1, and x being 1/3 goes with y being 1/3. That means I now have 4 critical points that I need to investigate. My next step is to find the discriminant. To find the discriminant, I'm going to need the second partial derivatives and the mixed partial. Remembering the mixed partial doesn't matter which order you go in, you should get the same one, so whichever way seems easier. Finding the second derivatives, we get the second partial of x is negative 2y, second partial with respect to y is negative 2x, and the mixed partial is 1 minus 2x minus 2y. You should pause here to go back and look at our original computations to verify that that is in fact what you get, right? The second partial of x, I'm treating the y's as constant. That's where I'm left with the negative 2y. And then the second partial of y, the x's become constant, and I'm left with negative 2x. For the mixed partial, I can either look at the partial with respect to y and take the derivative with respect to x, or vice versa. So verify that you can get all of these computations. And now we're going to plug in, I like to simplify an expression, as the book is doing as well, for the discriminant first, and then it makes it easier to plug in. So our second partial with x times our second partial with y minus the mixed partial squared, and we end up with this expression right here. So we have our 4 critical points to test. I'm going to plug them in also to the second derivative with respect to x, because remembering if my discriminant is positive, I need to specifically check the second partial with x to see if it's positive concave up, I've got a minimum, negative concave down, I've got a maximum. And if the discriminant itself is negative, I then have a saddle point. So in this case, we end up plugging in 0, 0 gives us negative, saddle point, 1, 0 makes the discriminant negative, I get a saddle point. 0, 1, I get the discriminant is negative 1, again a saddle point. 1/3, 1/3, the discriminant is positive, which means it's a max or a min. So I go back to check the second partial with respect to x, that's negative, implying if I zoomed in on the quadratic approximation at that point, it would be concave down, making that critical point a local maximum. So I end up having 3 saddle points and 1 local maximum. I would encourage you to pause and open up a graphing application and look at the graph to verify that that is in fact the case. That's what you will see. So looking at the next ones, I would encourage you to try part B here on your own and see and verify that you can do these problems, and D. And then let's also look at starting number 2 together in our last 2.5 minutes on the video here. So this is exactly the same, a similar function that we've already done, or that's already been done in the examples, but now we're going to put it on a closed and bounded region. So that's our new theorem from 15.2. That's a little bit different than what we talked about yesterday in 15.1, and that any function that's on a closed and bounded region will have a global max and minimum. And either it will be a critical point or it will be on the boundary. The boundary is a little bit harder to test now because the boundary has an infinite amount of points. So you have to do it a little bit more analytically and kind of look at what's going on. So the first thing we did is find the critical points by setting the partials equal to 0. And then I'll let you verify that on your own. We end up with the critical points at 2, -1 and -2, -1 as well. And also 0, 0. So we have 3 critical points, plus we have the boundary. So in this case, the only critical point that's going to be relevant is 0, 0 because I'm stuck inside my green square. The other critical points over 2, down 1, and to the left 2, down 1 are not in the closed region I'm looking at. So either 0, 0 is the global max or global min, and or the global max and global min will be on the green closed boundary. So now we can see from the contour diagram that the global minimum value is 3 is gotten at the point 0, 0, and that means our global maximum will be on the boundary. So by using a contour diagram, I don't have to check an infinite amount of points. I can come and look and see this point, these 2 corners over here are where I'm going to get my global maximum. Without a contour diagram, you would have to do a lot more analysis by using algebraic substitutions if x equals 1 or y equals 1 and plugging in some of those boundaries into this function and starting to see if where your function is growing and where your function is decreasing in order to establish where you would have the global minimum and maximum. All right, so back in the saddle, finish doing all of those activities from 15.1 and 15.2. Check your work and either Zoom into office hours or email me any questions on those, and then you should be all set to attempt the 15.2 homework. See you tomorrow.